Section 5.3, two-way tables and Venn diagrams. When it comes to probability problems, when we see the word or, we know that we're adding two different probabilities. However, not all or problems are the same, and it really comes down to whether the events we're talking about are mutually exclusive. So let's say we're at a restaurant and we're asked, do you want soup or salad with your meal? In this case, we have mutually exclusive events. We can choose the soup or the salad, but we can't pick both of them. There's no overlap between those two events. Compare that to ordering a coffee. When you're asked, do you want cream or sugar? In this case, you can pick just cream or just sugar, or you can choose both of them. All right, these are not mutually exclusive events because there are some people who will choose both of those two events at the same time. So let's do a few problems with a data set of college statistics students who were asked, can you taco tongue? Can you evil eyebrow? We'll start off by finding the probability that someone can evil eyebrow. We see that on the left there. We see yeses here. And if we were to add these two numbers together in that yes row, we'd get 62. And the probability is going to be that number over the total number in our sample there. So 31% chance. Part B, find the probability that they can taco tongue and evil eyebrow. Yes for evil eyebrow. Yes for taco tongue. And we're looking for the intersection of those two. The students who can do both would be those 42 students out of the 200. Now for the last one, probability that they can taco tongue or evil eyebrow. Now when we see the word or, we're always treating it as the inclusive or, meaning that they can do one of these or the other or both of them. It's like the cream and sugar coffee order that we talked about a slide or two ago. So we have 62 students that can evil eyebrow, 149 that can taco tongue, but we're not able to just add these two together like we did previously. And the reason being is that these are not mutually exclusive events. Okay, if we were to just add these together, we're double counting the people who can do both. So in other words, this 149 came from these two numbers added together. This 62 comes from these two numbers added together. All right, and we can see that if we were just add that 149 and the 62, that group that can do both of these gets counted twice. So we're going to do what's called the general addition rule, where we add those two things together, just like we did up here. All right, but after that, we're going to subtract out the number of students who are in both of those categories. All right, and that's the intersection or the overlap of those two categories. We could also do it just logically. All right, if we just look at all of these and say, all right, we have these 62 people who can evil eyebrow. The only other people that we need to add on to that are the 107. Okay, so this method and this method will both give us the same results. That's called the general addition rule. We always need to use this rule when we have events that are not mutually exclusive, meaning that they can happen at the same time. And again, we add each of those probabilities together, and then we subtract out the overlap that's counted twice. A 2018 survey suggests that 51% of US teenagers use Facebook, 72% use Instagram, and 38% use both. If we randomly select a teenager, what's the probability that they use Facebook or Instagram? Again, this is always an inclusive or, meaning we're including the students that use both of these. So to use the general addition rule, we're going to add those two probabilities together. Right now, if we were to just do that, we would end up with a probability that's over 100%, okay, which is an impossible value to get for a probability. That's actually the wrong one there. It's this one up here and this one that we would add. So if we get a probability that's larger than 100%, we know that we made a mistake. In this case, we have to subtract out the 38% that use both of these because that's double counted. All right, and our answer is 85%. So we did this problem as a two-way table, but a lot of times we'll use a Venn diagram instead. So let's create a Venn diagram, which has our two overlapping circles, and we'll start by defining our events. So we have that yellow circle, which is taco tongue. The blue greenish circle is the evil eyebrow. And we always put in the overlapping section first. So we want to put in this green section here, all right, with the part of the table that can do both. All right, after that, we can just fill in the remainder. So evil eyebrow, and no taco tongue is the 20. All right, in the yellow circle are the students that could yes taco tongue and no evil eyebrow. Is that 107? And the only thing remaining is the people who could do neither. And that's going to go outside of our circles there. All right, that 31 completes the sample space. So the total adds up to 100%. When we're looking at our Venn diagram, we have our event inside the circle. Everything outside the circle but remaining in the box is the complement of our event. And again, that'll add to 100%. So the total of our box in our Venn diagram should always add to 100% everything that can happen. When we're looking at the overlapping portion of our two circles, that's called the intersection. And we refer to that as A and B. And we use this little symbol there, kind of like an N or an upside down U. When we're combining the two, we're finding the or problem. All right, either or the other or both. That's known as the union. We read it A or B, okay, and we use that U for union. So again, and problems are talking about the intersection, the overlap of those two circles in a Venn diagram. An or problem is the union or the combined circles, including the center. U for union, N for intersection. And we could write our addition rule as follows there. Now, in most cases, we won't have a two-way table to start the problem. Instead, we'll get text like this. So let's change this text into a Venn diagram. We have a large apartment complex. 40% of the residents read USA Today. 25% read New York Times. 5% read both. So we always want to start off with our overlap. That 5% is going to go in the middle here. I'm going to write it as a decimal, 0.05. Okay, we'll make this side the USA Today side. All right, now if there's already 5% in that middle section, we can't just put a 40% over here because now this whole circle would total 45%. So we have to subtract that out. There's 40% in total, which means there's 35% over here. Combining with that middle part totals the 40%. All right, for the New York Times, 25% read New York Times. So there's going to be 20% over here combined with that middle section gives us that 25%. All right, if we add all three parts of that inside the circles up, we have 35% plus 5% plus 20. We get 60%. That leaves 40% that read neither. Part B, find the probability that a person reads exactly one of the two papers. So in this case, we have the people reading just USA Today or just New York Times, and we're not going to include that 0.05 where they read both, and we get 55%.